Hello, David. Hi. I'm pleased you got back last week.
For 39 years, from 1980 until 2019. He joined the Steam Turbine Design Department in 1982, rising to Head of Turbine Design in 1991 and Head of Turbine Generator Engineering in 1994. Parsons became part of Siemens in 1997 and was joined by Westinghouse in 1998. Reorganization led to the majority of new generator work moving to the Westinghouse site, while the majority of steam turbine work moved to the Milhem and Ruhr and Newcastle sites. In 1997, Geoff was appointed Chief Turbine Engineer at Siemens Power Generation. On retirement in 2019, with Siemens' permission, he began to document the Parsons history so that it can be preserved in the Tyne archive and other institutions. So thank you for coming this afternoon, Geoff, and over to you.
Good afternoon, everybody. I hope everyone can hear us. If there's any difficulty with audio, then please give feedback to the organisers and we'll put it right. A lot of people are familiar with Sir Charles Parsons in terms of his primary product lines that he developed. Steam turbine generators figuring as one of the main ones, and marine steam turbines as a second. But what we're going to do today is we have two talks lined up, one now and one in the evening, related to another aspect of Parsons and of the company founded, because the work was carried on past the day that Charles Parsons passed away. So this is another aspect which is a primary activity of the company, which very few people know about, and this is the development of gas turbines. So the first talk this morning will be a discussion about the first industrial gas turbine in the UK. You can see a photograph on screen at the moment, and I'm going to go through some of the details of it and give you the background to it. So this was developed at the Heaton Works plant of CA Parsons Co Ltd in Newcastle. Now, where does the story start? The story starts back in the 1880s. So maybe this is not so well known because there are some of these details recorded in history books and on the internet where people get things confused. So I just thought I'd give a very quick summary just to iron this out so you know what the earliest days were. So Charles Parsons developed the first steam turbine generator in 1884 while he was a partner with Clark and Chapman in Gateshead. Before he did that, so before the steam turbine generator, 3 years earlier, he developed a gas turbine, and nobody seems to know about it. Very few people seem to know about it. So we're going to see that on the next page. In addition to that, if you're going to develop a gas turbine, you need the key elements, compressor, turbine, etc. And he developed a new type of compressor, the first of its type in the world. And that we're also going to look at quickly before we move on. But most of the work that was done to create the first industrial gas turbine was in the 1930s and 40s. And unfortunately, Parsons passed away in 1931. And the person who really took the work on from that point was Dr. Robert Dowson, who was Parsons' chief research engineer. So Dowson was doing an awful lot of work in the 20s and 30s, which led to a commitment to start building the machinery in the 1930s. So we're going to see all of that, and let's go through it. Now, there are a lot of slides. I'm one of the people who believes I'm going to give a talk It's better to give more information than less. And obviously, I may go too fast, or you may want to spend more time looking at the information we've got in the photographs. This is why I provided copies of the slides to the organizers. So if I do go too fast, obviously you can tell me to slow down. Or if you wish, you can request a copy of the slides afterwards, and then you can browse them at your leisure. And this, for that reason, there's a lot of wording on some of the slides, too much for me to read out in a talk, but information you might be interested in to browse afterwards if you wish. So Parsons' first gas turbine was a device that looked in principle like this. The only image that exists is a pencil sketch in a notebook. There are no other images of it, so I've had to recreate using modern graphics something that illustrates the principles, but it powered torpedoes in 1881. So what you had was a disc with vanes formed on the outside, which were in effect turbine blades. There were impulse turbine blades directly coupled to the propeller, and that drove torpedoes. Where did the gas flow come from? It came from burning rocket propellant. So the rocket propellant was simply a fuel that was used to produce a high velocity steam flow, which drove the wheel. Now, in many, many history books, people pick up on the words rocket propellant and don't go beyond that, and then describe these as rocket-powered torpedoes. So they've got that completely confused. They weren't. It was gas turbine powered, but it used rocket propellant as the gas flow. So when Parsons developed the steam turbine generator in 1884, and he created a patent, which I've shown the first page on the right-hand side of this slide, not only did he patent the steam turbine, he also patented the gas turbine at the same time. Because even from the 1881 work, he realized that if he had had a compressor or a pump of appropriate duty to put at the front, he could have had a gas turbine that just could have kept running and could have been used for industrial power purposes. But at that time, the type of compressor he needed didn't exist. So let's just touch for a moment on what do you need if you want to develop a gas turbine. The most important parts are three key things. One is very efficient compressor blading, very efficient turbine blading, and the very bottom line, the wording on the screen points it out, that the power you're going to have delivered to a generator or a pump or whatever you're driving is the difference between the power produced in the turbine blades minus the power absorbed by the compressor. So you want both sets of blading to be as efficient as possible so you get the maximum power output. And you also need suitable high temperature materials which can handle the firing temperature in the combustion chamber. So for those three elements, one of them was very easy to obtain, and that was the turbine blading, because CA Parsons Co were putting enormous efforts in all the time to develop steam turbine blades. And the blades you can see on the left date from 1900. They're actually from the Scottish Maritime Museum. They're actually marine turbine blades from the SS King Edward. But that is a blade called the 400 series blade that was used extensively up until the 1930s, and it achieved an efficiency of 90%, excluding tip leakage. In 1933, the blading on the right was introduced. This was named the 600 series blade, and this raised the efficiency level to 93%, which for those days was quite a good performance level. And either of those blades would be perfectly suitable for a gas turbine. It's the 600 series blade on the right-hand side that was actually used in the Parsons gas turbines. So that was easy. Compressors, not so easy. Now, one of the first things that Parsons did was he observed in the factory that when he had a steam turbine, and for some reason it was running backwards, that the steam turbine acted as a pump. It was blowing air out when the pipes were off. So he investigated this between 1897 and 1900 to try and optimize it and convert the turbine into a compressor. And this is the world's very first axial flow compressor. There were none before this work. This is the very first one. ever produced. That's the only image we've got. As you can see, it's completely boxed up, so we can't actually see what's inside it. But the next slide will give us an example. So the photograph, which I hope you can see on screen now, shows the second machine to be built in 1901. And so while the first one was an experimental compressor that was kept at the works for investigations, the second machine to be built was a production machine for a customer to go into service. And as you can see, it looks remarkably like a modern axial flow compressor with open-tipped blading, freestanding blading. Now, the way that the blades operated, this all had to be investigated and researched from scratch because there was no previous experience. And the type of blading that Parsons adopted was called plano-convex. In other words, the blades were flat on one side. So you can see the fixed and moving blade rows here. These are low camber, high stagger angle blading. They worked well for 1900, but they only achieved an efficiency of about 60%. So the company sold a number, but it wasn't high enough for a gas turbine, nowhere near high enough. We needed something better than that. By 1909, centrifugal compressors were in use within the industry generally. Parsons didn't invent this. I think these were attributed to Ratto. The centrifugal compressors in 1909 were achieving efficiencies of 70%, which is better. So Parsons did make these, but and made more of them than the axial flow compressors, but the efficiency was still not good enough for a gas turbine. Now, this is where Dr. Dowson steps into the picture. So Robert Dowson joined Parsons in 1911, and by 1917, he was in charge of turbine and condenser design. In the 1920s, he became manager of the technical development department, and he was responsible for all mechanical research. And that includes the development of all blading, both turbine and compressor. And he subsequently became chief research engineer. This is a photograph of him in the Home Guard in World War II. It's the only image I've got, I'm afraid, at the moment. I'm hoping to find others, but you can see him. He was a lieutenant in the Home Guard. So Dowson got to the point where in the early 30s, he believed that compressor blading could achieve a high enough efficiency to make a gas turbine worthwhile. This was about the time that Parsons passed away. I suspect, since Dowson's work still exists and it describes developments in the 1920s, that Parsons would be aware that Dowson was pushing in that direction and must have had his sanction to do it, but Parsons never saw it completed because he died, unfortunately. But Dowson was a real powerhouse behind this, driving the developments through. With a team of people, of course, but he was a real power behind it. So he reached a point where he said, we should build a compressor now with the latest blading. And this is a photograph of it. This photograph is from 1935, but was created, 1936, the date's on the photograph, but it was actually created first in 1935. This was an 8-stage axial flow compressor using blading developed within Parsons. The casing it's in belongs to an experimental steam turbine. Those who know anything about the Parsons history will know that experimental steam turbines tend to be named after members of Charles Parsons' family. And this little turbine, the casing, belongs to a unit called Alice, which was created in 1901. So Dowson took the turbine internals out and inserted the compressor rotor. At the time this was developed, steam turbine blades had shrouds with an axial sealing fin, not radial sealing fin. And the reason this was done is because people couldn't predict transient radial deflections like ovality. And therefore, if radial sealing fins were used, there would be rubbing. So axial fins were used instead. And thinking that it was good for turbines, it would be good for compressors. That's what was built. And this is called compressor number 1. This is a picture of the blading. You can see it is faint, I've done the best I can to reproduce the original sketch. All of these sketches come from the original development files. And you can see that each blade row had a single sealing fin. The thrust bearing was movable, so you could actually open the clearances when you're running the machine up and heating it up. For a compressor, of course, that's not so relevant. And then you could tighten the clearance. So it means that even on a compressor, that sealing fin clearance was adjustable. And you can see the aerofoil profiles are not plane or convex anymore. They're not flat on one side. They are true aerofoils. But they're still using low camber, high stagger angle designs. That's the efficiency that was achieved. So where in 1900, an axial flow compressor achieved 60%, compressor number 1, and it is a small scale compressor which would affect the results, is now 70%. So it's good, but not good enough. So Dowson and his team were doing an awful lot of research of their own and reading all of the publications and papers that were being released in the industry. And in particular, linked up with Hayne Constant, who's a very famous engineer at the Royal Aircraft Establishment, who was also investigating airfoil profile and compressor blading performance. And this led to compressor number 2. So this is a photograph, this is a sketch of compressor number 2. And as I said, we were now taking some advice from Hayne Constant and bouncing ideas. Dowson and Constant were bouncing ideas off each other. And this is the way the machine developed. What happened now was they dropped the Parsons blade and went for an airfoil called RAF number 27, airfoil profile number 27. And the shrouds were eliminated, going for a more conventional, by modern standards, open tipped arrangement. Here we can see a picture of it. This is the compressor is opened up. In the foreground, the steam turbine that drove it at the side is another experimental steam turbine. We saw Alice a moment ago. This is a steam turbine from 1928 called Alicia, which was slightly larger, and that was just used as a motor to drive the compressor. Okay. So this is 1937. Now, when it ran, it didn't perform quite as well as they wanted, but they realized that the real shortcomings were in the outlet chamber. The outlet chamber wasn't large enough, and also the diffuser wasn't achieving a high enough pressure recovery. So they adopted several alternative diffusers and came up with the design that you have here. And now the performance jumped up quite significantly. The other thing that happened was we learned on the earlier compressors that where the inlet's concerned, you shouldn't have a rotating surface because it upsets the flow going into the first blades. You should have a stationary flow surface. But here we can see modified compressor number 2. Like I said, it was built, I think, in 1938 when it was built. This is photographed in 1939 in May. Compressor on the left and Alicia steam turbine on the right. There's a view close-up of the blading. So as I said, it's the RAF number 27 profile, made in I'm not sure how to pronounce it, duralumin. Is that the right way of saying it? There we are. You can see the picture paints 1,000 words. Performance results. The overall efficiency of the whole compressor was about 80%, but that includes the inlet loss and the diffuser efficiency. The stage efficiencies of the blading were about 85%. So now we had a result. It had taken a little while, but now we had a compressor that was good enough to build a gas turbine. What happened was it didn't end there. The relationship between Parsons and the Royal Aircraft Establishment went very, very well. And they continued exchanging thoughts and ideas on this. And for example, in 1941, this is when the Royal Aircraft Establishment installed this, which was the first supersonic wind tunnel for testing cascades of blades within the UK. And Parsons and RAE actually worked together on this. obtaining readings on blading in the velocity range Mach 0.5 to Mach 1. And it's on record that they talk about something like 100,000 readings we've taken off this collectively, a huge body of work. And what happened now was overall compressor efficiency now rose from 80% more to 85, 86%. Starting to look very healthy indeed for building a gas turbine. There is a report which states that a lot of people have a view of the principles in which the compressor was designed, such as free vortex flow. What actually happened in 1941 between the RAA and Parsons, they abandoned some of the established principles. And there are 5 points on this slide which determine how they decided to design the compressors in the 1940s. So it was a constant axial air velocity component at all blade heights. Work done per stage was made constant at all radii. Principle of free vortex flow was abandoned. Stator blades were not twisted. Remember, it was very expensive and difficult to make twisted blades. When they studied it, twisting the stator blades had very little benefit. Twisting the moving blades had a very great benefit. And they introduced this thing called twisted and flattened blades, which means that the outer part of the blade, towards the outer flow boundary, was flattened. The camber was reduced, which improved the performance of the blades. Okay, that was a rush through compressors. So we've now got turbine blades achieved, suitable. We've got compressors which are suitable. What about materials? In the 1930s, of course, there were a wide range of austenitic stainless steels, and these could allow temperatures up to 1200 Fahrenheit or 650 centigrade to be used. When the Frank Whittle built his first engine and flew in the Gloucester, I think it was the E2839, that triggered, pardon me, the development of nickel chrome superalloys, in particular mnemonics 75 and 80. And they started to become available, but in very small quantities. At this time, we're now, really talking, the time I'm really going to focus on 1941 onwards, and of course, we're in the middle of the Second World War. So the highest priority were the early jet engines. They got the first priority for these exotic materials. But an industrial gas turbine was still seen as a war benefit, because achieving efficient use of fuel was quite a high priority. So by the time this was occurring, everything that was done in industry was largely under the approval of the UK government. And they said, yes, go ahead with the gas turbine development for industrial purposes, but you're going to have to limit how much of these new materials they have. We're going to give the great majority of it to the jet engine people. So that's what happened. It meant that we could use small quantities for the combustion chambers and flame tubes and some of the hot gas ducts, but we couldn't make the turbine rotor casing out of these materials, and we couldn't make the majority of the blading out of these materials. So what that did was it meant that this first gas turbine was going to be limited for long-term tests to 1050 Fahrenheit, that's 566 centigrade, but it could run for short periods at 1200 Fahrenheit, 650 centigrade. Now, I'll put this table in. I don't intend to read it out. I think I'll take up the whole duration of the talk to talk about it. But if you want a copy of the slides, you can see the actual materials that we used. Rec 78G, 18B, if you will. Around in those days, these would be quite well-known materials, although they're less well-known today. And mnemonic 75 and 80 are at the bottom. Those of us who worked in the power generation industry will know mnemonic 80A, which is a modified version that did not yet exist. It wasn't far in the future, but it didn't exist at the time this machine was built. Now, I've taken that table and I've just reduced it down a little bit to give an idea of where these materials came from. As I said, the Rec 78 came from the power jets development, as the G18B that was used in the WWII engine. And the mnemonics I've already mentioned followed the flight of the first British jet aircraft. Okay, You can tell I'm trying to push through this fairly quick. I'm hoping I'm not rushing it too much. But we've gone through the first three elements. We have efficient compressor blades, efficient turbine blades, and now we have some suitable high temperature materials. So the last parts of the picture before we put the machine together is to develop the combustion chamber and an exhaust gas heat exchanger. If you build a gas turbine without an exhaust heat recovery device, then the best cycle efficiency you're going to achieve is going to be about 20% and possibly less. So to be competitive against steam turbines, diesel engines, and other prime movers, the gas turbine had to have an exhaust heat exchanger. The sort of figures that we're aiming for are stated here. These are from the original reports. 84% compressor efficiency, turbine efficiency 86, combustion efficiency 97, and a peak turbine inlet temperature of 1200 centigrade, with 75% of the exhaust heat being recovered. So for the first machine, the demonstration plant in effect, that is what they were going to go for. This is a view of the rig for the heat exchanger. So you've got the diagram on the left is very complicated. I'm just going to simplify it by saying there are two air circuits there. There's one with a combustion chamber, which obviously the gas is going to have the combustion products mixed in it. And that's the one that creates the hot air. And then there's a separate closed circuit with clean air in it, where the heat exchanger transfers the heat from the combustion gas to the clean gas. And that's how it was worked. Parsons actually created the combustion chamber for that, and it actually burnt, I think it says on here, again, we're in the middle of wartime, this is September 1942, discarded varnish from the Parsons transformer shop. So that's what was being used. There was a fuel that was available and otherwise might have gone to waste. Combustion efficiency was 99%, but the heat exchanger itself looked something like this. Now, remember, Parsons is coming from a steam turbine background, and unsurprisingly, the heat exchangers look like steam turbine feed heaters. Again, it's a tube and shell heat exchanger, so there's no reason for why not, except using air, which is largely not much above atmospheric pressure. The heat transfer coefficient with air is much lower than with steam, so there is a challenge there. And when they built this, the first heat transfer rate they achieved was 22.7. I put it in modern units, watts per square meter centigrade. I used to work in BTU per hour square foot Fahrenheit, and it's a nice round number of 4 in those units. That's what was achieved when they hoped to get 8. So it's about half of what they expected. They changed the tube support plates, which guided the gas flow, and got it and improved it by 25%. So the heat transfer coefficient was a little low, but it did recover 71% of the heat in the combustion air. So it wasn't far off target. And as a very first attempt at building an exhaust heat recovery device, that wasn't too bad. Now, subsequent refinements did raise it to the 75% level. I haven't put them on screen because you wouldn't be able to tell the difference much from what you're looking at now. It would be a 2-pass tube and shell heat exchanger. Now the combustion chambers. Again, this is a field where there was no precedent. Parsons had to create the combustion chambers for themselves from scratch. Now, this was the very first one which was developed as a trial for the gas turbine. Fuel pressure, fuel was high quality distillate oil, and this was supplied at high pressure, 2,000 to 4,000 pounds per square inch, and then subsequently low pressure. So they wanted the ability to run at either condition if they could. What happened with this? This was carried out in early 1944 with the tests in November 44. And what they found was there no problems burning the fuel. They were getting good air to fuel ratios were being supported. Fuel atomization was good, very little smoke. But the only thing was, at the outlet of the ducts, there was an uneven temperature distribution. So there was a difference in temperature of 250 Fahrenheit, that's 140 centigrade, across the width of the duct. And that was too much. Bear in mind, we don't have much good material. You know, the use of pneumatic and austenitic steels is highly restricted. So you can't afford to have temperatures uneven within the duct. That's the test rig. So what happened was it then led on to two more types of combustor, which you'll see on this slide. At the same time, the company was under some pressure to change from high quality distillate oil, which was very hard to obtain at that time, to what was called pool oil. This is a type of oil that was more commonly used in power stations in the war years. So it was a mixture of high quality oil with coarser grades of oil, and it was actually quite variable. So that's what happened. We changed the development to start using pool oil, and this is the first type of combustor that was produced. So again, it was getting slightly better combustion, but the temperature difference from one side of the outlet duct to the other was still 250 Fahrenheit. So it didn't achieve the result. That was called combustion chamber number 1A. So they then changed to the design on the right-hand side, and you can see that the cone of at the beginning of the flame tube has been changed to a flat ball, and some other changes, and that just made it worse. So we're now getting smoke and heavy deposits being produced. And they need to be, according to the report, it says they concluded they needed more turbulence in the combustion zone. If you don't mind, I'm going to sit because I'm getting a pain in my back. Sorry about that. Right, that's better. And then moved on to combustion chamber 1D, and this was the final design. This is the one that worked. So what they did here was they went back to a conical, a flame cone, and the chamber was extended to twice its original length. The inner cone was emitted from the outlet end of the chamber, and a deflecting plate was inserted. What Parsons had learned was that the airflow entering the flame area had to be divided into three portions. You had the primary air, which comes in beside the burner, where you swirl the air. You literally got a set of vanes creating swirl, because what happens is that's where the flame is created, and by having the gas folding back on itself, the flame was coming back to ignite the next portion of fuel in there coming in. So that kept the flame going. Then you had secondary air, which was injected where the flame tube ends and brought in. And what they did there was they wanted to, that was used to stabilize the combustion without chilling the flame too much. So they didn't want to extinguish the flame with that. The tertiary air, if you see the flame tube, there's an outer casing and then the flame tube within it. So the tertiary air flowed between the two and therefore kept those items cool. And then at the end of the flame tube, it came in through openings to mix with the flow, so you achieve the final outlet temperature, the turbine inlet temperature that you want to operate at. And the temperature distribution is up on the top right-hand corner. And again, it was a much better result, 100 Fahrenheit, not 250 Fahrenheit. It was 56 centigrade from one side of the duct to the other. So again, they were happy with that and decided to proceed with that as the design. So we got all the elements. We just have to put it together and run it. That's the next thing. So what should they build? What they decided was they would build the smallest size of gas turbine, which would demonstrate the principles sufficiently to say, yes, gas turbines are worth building and developing further. Everyone knew that the bigger the gas turbine you built, then the more efficient it would be, the better performance. And you couldn't build it too small, otherwise just the practice of making it too small would prevent you from achieving a viable result. So I decided to build a 500 horsepower machine, that's 373 kilowatt, when running at 1200 Fahrenheit, the maximum temperature. It was an open cycle gas turbine. The elements are in the diagram, but it is just a compressor, a turbine, a combustion chamber, and an exhaust gas heat exchanger, driving a dynamometer. The project was jointly sponsored by the Parsons Marine Steam Turbine Co. because they wanted to use gas turbines in ships when CA Parsons was going to use this for mechanical drive and power generation. Unfortunately, in the very bottom of the slide, you can see in the 20th of June 1944, Robert Dowson passed away. He wasn't a war casualty. He died of natural causes. I think he was around 59-year-old when he passed away. Another very capable man took his place. This was Dr. Tony Bowden, who became the Chief Research Engineer. And he was another powerhouse who was very much committed to developing gas turbines for all kinds of applications. We're not going to talk about all of them today, but the kinds of things that happened were for power generation, a railway locomotive gas turbine, a gas turbine to power a main battle tank, the first in the world of that type, etc. So, again, this is where the baton passed to Tony Bowden, and he handled it well. So here's the final design. Let's just have a little look at it. The compressor design was a 25-stage design with an area in the center where you could release air to prevent surging. So there's this anti-surge valve fitted. But another thing that was done, you can see labeled on there that there was a water jacket put over stages 11 to 25. That's the outlet end of the compressor. The whole idea here was to try and achieve isothermal expansion, where the blades themselves act as heat sinks, and the blades were like fins conducting heat to the water jacket to remove heat. Also, the water jacket would chill the cylinder and therefore cause the clearances, the running clearances, to tighten slightly. The speed of the machine, 6,000 rev per minute. I won't read out all of the data there because you can read it at your leisure if you get the slides. But there was the RAF 27 profile again. Compression ratio with cooling was roughly 4:1. The target efficiency was 82.75%. So it's quite low compared to a large size machine, but that was the nature. We're going to use this as a small prototype to demonstrate the principle. Blade heights were generally 2/3 of an inch to 1.5 inches. Carbon steel shaft, brass casing for conductivity, thermal conductivity, and the blade material was duralumin again. There's a picture of it. Again, Parsons is a steam turbine builder. So unsurprisingly, they built the compressor like a steam turbine. That's not to be underestimated. Anybody who works in turbine design always knows that the most important thing about any machine is reliability. You can have the most efficient machine in the world and it's worthless if it breaks down and it's not running. So one of the things that all turbine builders do, and we still do it today, is to make sure you use a form of construction and materials and use experience that says, yes, this should withstand stresses, minimize deflections, minimize ovality, etc., and run well. So since the only experience Parsons had was the steam turbines, that's what they applied in the construction. It wasn't necessarily a bad thing to do, but it made it a very heavyweight looking casing compared to the aero-derivative gas turbines that followed in the following 20 years. So, as I mentioned, this is just a slide on the water cooling. There were actually 4 approaches to isothermal compression that were initially investigated. The water jacket. Another was a compressor with intercooling between sections. Hollow cooled compressor blades were considered, and injecting a mist of water was considered as well. It was the mist of water that Parsons started developing first, and then it didn't work out. So what they found was if injected water, it would drop the outlet temperature from 123 to 82 Fahrenheit and increase the mass flow rate by 3%. But the water reacted with the fuels, the pool oil, and started producing sulfuric acid. So that's why they swapped to the water jacket. But the notices, so I'd like you to bear this in mind. I'm going to come back to this. I think it's pretty important. Just that water jacket improved the compressor efficiency by 1%, as well as boosting the compression ratio and the airflow rate. So it was quite a useful thing. But there are consequences, so please bear that in mind, and we're going to come back to that in a couple of slides' time. This is the turbine casing. It's an 8-stage turbine. The first 4 stages were freestanding, and the last 4 had lacing wires to make sure the blade vibration characteristics were good. Inlet conditions were about 51 psi absolute, 1050 Fahrenheit for most of the time, but 1200 Fahrenheit for short periods. Shaft diameter 16-inch, and it was made of only carbon half moly material. Carbon half moly was introduced about 1930 for steam turbines when temperatures went from 700 Fahrenheit, which only required carbon steel, to 800 Fahrenheit. And when we built 60 megawatt units in the 1940s, steam turbines, carbon half moly was suitable for 900 Fahrenheit. For 1,000 Fahrenheit steam turbines, we went to one chromoly-vanadium, a completely different class of material. Of course, that was 1950. The material didn't exist when this was built. Carbon half moly was the best that was available when you didn't have austenitic steels you were permitted to use. So it's really a material for 900 Fahrenheit, and it was being used here at 1050 to 1200 Fahrenheit application, and that limited the running hours. There's a picture of the machine. Again, it looks like a steam turbine. Very simple design, really. I don't have to say much about it because it's just open-tipped freestanding blading with lacing wells at the back end. We need to know how some of the materials would react. So we did use austenitic steels and mnemonics in the first row, the highest temperature blades, to say what would happen in terms of erosion, scaling, and distortion. But there may be only 2 blades of each being put in, or 3 or 4 blades at most, just to see how they reacted. And if you look at the scores, first, second, third, and fourth, that's how these worked out. So Immaculate 5 austenitic steel gave the best result in terms of mechanical resistance, with mnemonic second. So here I have the machine. There's the turbine inlet and outlet on the turbines on the left-hand side. The valve is a runaway control valve. So when that valve opened, it bypassed air from the turbine inlet directly at the exhaust to make sure we didn't have an uncontrolled situation. Compressor is in the center. And then we have the Froude dynamometer and the starting motor on the right-hand side. That's what it looks like in the Parsons Works in Newcastle. So I've marked some of the flow directions. If you see in the bottom left corner, you can see a large metal canister lying horizontally. That's the combustion chamber. Out of sight at the back behind the gentleman who's crouching down under the floor is the exhaust heat exchanger, which you'll see in a moment. There's another perspective with the starting motor nearest to us and the compressor at the far end. You can see the combustion chamber on the right. It's quite small. But if you look on the left, can you see that the chamber that's there is the full length of the photograph? That's how large the exhaust gas heat exchanger had to be to provide enough surface area with a low heat transfer coefficient. The pipe is horizontal. Now, this picture isn't horizontal, but the pipe is horizontal, is the compressor air inlet coming from a bank of air filters. We have one color photograph. So again, this is around about 1945, 1946. The machine ran for the first time in December 1945. Performance results. It immediately met its performance target, which was good news. So a 500 horsepower motor achieved 511 at 1200 Fahrenheit. Obviously, as the temperature was lowered, the power output reduced. Compressor efficiency was 2% below performance. This is attributed to non-uniform fluid inlet, something that was addressed in later machines. Heat exchanger achieved 77% heat recovery, 2% better than target. Oh, and the turbine was 85.4% based on shaft power, 84% measured at the dynamometer. They were good enough to say, yes, this is a success. A gas turbine can be made to work. If it works on this scale, it's only going to get bigger, better as we go bigger. This is another curve which I've included. There were some lessons learned. What you find is the speed of the machine when the combustion chamber was lighted was 2,970 revs per minute. Maximum speed was 6,000. So that was kind of a working range, but the compressor approached the no load line of the compressor approached the surge line at about 4,600 revs per minute. So that limited the range of operation. Two things contributed to that. One was the fact that carbon half moly was used for the rotors, limited the dimensions of the machine, so it didn't have freedom to design what they wanted. But also Parsons made a mistake to a degree in matching compressor and turbine. So we learned the lesson, and that was again put right on the next machines that were built. Let's get this some more. Can I just check the time with you, John? How much?
You're okay.
Sorry?
Quarter past 3.
Quarter past. Okay. So we've really described the development of the machine up to that point. I could stop, but there were some other interesting things, historically important things, and I'm going to show them now. It's not a huge number of slides, but you might be interested. So some of these were the operational issues. When the machine was very first run, we didn't have the delivery of the austenitic and pneumatic materials. So we actually made the flame cone out of cast iron and the body of the combustion chamber out of either I think it says carbon steel or carbon half moly. Unsurprisingly, the flame cone distorted, but it performed well once we had the right material. There were 3 occasions when the compressor blading was damaged. The first one, you can see some of the blades at the outlet end, stage 25, have been knocked off. What happened here was there was a run where the water jacket was supposed to be out of service. Somebody left the water flowing slightly. So instead of filling the jacket completely with water, there was a little river of water at the bottom. So the casing was cooled asymmetrically and it distorted. And it rubbed the blades. This is another occasion. Again, these are about 1946, 47. And this is a case where, again, you can see a few blades have been broken off. This is where somebody increased the flow through the cooling jacket to see what would improve. Well, as I mentioned, as you cooled the compressor casing, it shrank and reduced the running clearances. So they had no method of calculating transient distortion effects in those days. So they just, unfortunately, the person who did it cooled it so much that, again, it took some of the blades off. Oh, let's get this going. But the big failure, it only ever happened once. They lost all the blades apart from a single blade roll. Now, what happened here was the inlet is at the far end on the right-hand picture, and there was a row of inlet guide vanes, and these were made out of brass and with thin plate. One of the vanes, a single vane, was downstream of a thick rib in the inlet. Disturbance from the thick rib caused that single vane to fail, and that cascaded a snowballing effect as debris from one blade took up more and more and more until all the blades are gone. In the 1940s, that was referred to as a haircut. In my time, in the 1980s, we call that a blade solid, but there we are. That's the only time that occurred. Now, what Parsons did was, of course, they designed out the feature. They got rid of the thick rib, they got rid of the brass vanes, and they could have just left it at that. But on steam turbines, they didn't tend to have a haircut if a single blade failed. There was always a risk it might happen, and certainly if one blade came off, it damaged some of the others around it, but it didn't take every blade off. And the blades in steam turbines were made of what was called stainless iron, which is a type of 12 chrome steel. So what they decided, just as a precaution, is from now on, instead of duralumine, they would use stainless iron for all compressor blades. Maybe overkill with hindsight, but it's important that it was safe, and that's what they did. So the rest of the work is now looking at fuels. Remember, there's not much experience of gas turbines at all in the UK at this time. There's some jet engine work, again, high quality fuels, but the power stations really were expected to run on lower quality fuels, and people wanted to know, the government wanted to know, whether the gas turbine could handle it. So Parsons received a contract to investigate running on residual fuel oil and burning coal directly in the turbine and putting the residue through the blades. And pool oil was also one of the fuels, low quality fuels that was tested, which I've already mentioned. So since pool oil was quite variable, one of the things we did was we ordered a batch of pool oil without a specification, just the same as a power station would do, and we could have absolutely anything within a degree of variability in that batch, and that's what we ran. So pool oil was the first focus, followed then by residual fuel, and then for 1949, the coal program. The problem with pool oil was it contained vanadium, and vanadium forms vanadium pentoxide, and this is a very sticky substance which persists at temperatures below 1100 Fahrenheit. And since this machine ran primarily at 1050 Fahrenheit, it formed a sticky gum on the blades. It also eroded them. It also affected them, chemically attacked them. But what happened was any ash that passed through adhered to the gummy substance and started to block the blades up. So when you see some of these photographs, the deposits that you see are often after only 40 hours, 50 hours, maybe as much as 150 hours, but not usually much more than that. Very short periods of time compared with a power station application, for example, when you would normally expect thousands of hours. So, residual fuel oil was worse than this, because residual fuel oil is what's left when you've completed the distillation of petroleum as far as you possibly can. And again, it can be quite variable, because to achieve an appropriate viscosity, you would mix it with high quality oil, but you had all the residue, and the residue contained all of the substance that created ash and chemically aggressive species in there. The amount of ash we're talking about is very small, so only about 0.01% to 0.1. So the pool oil was only producing 0.044% ash, but it doesn't take long for that amount of ash in a gas turbine to build up and cause a problem. But the payback, the end result would be enormous if gas turbines could be made to run on residual fuel oil, etc. That would be a fantastic result for the industry and in terms of money making for Parsons or other manufacturers. So a big development program was then undertaken. And the main areas were which elements produce ash, how was the ash produced and deposited, whether the elements could be eliminated from the oil before it goes into the turbine, if the ash levels could be reduced by changing the combustion process, or whether the ash could be removed after combustion before it goes into the turbine. And so what produces ash? I'm not going to read all those elements out. You can read them. A lot of different elements are of concern. Removal by distillation or use of solvents and other matters could remove them to a degree, but not enough to really make a difference. And the cost of doing it made residual fuel oil as expensive as using high quality distilled oil in the first place. Different combustion chamber designs were tried and chemical additives were tried. And again, these had an effect to a certain degree, but again, not enough to succeed and still put the price up to the price of high quality distillate fuel oil. Removing ash was attempted using cyclone separators, electrostatic precipitation, pebble bed filtration. Large particles bigger than 10 microns could be removed. They're the ones that cause erosion, but not those the smaller ones which form deposits. And finally, blades were designed with larger spacings, etc., to try and accommodate the buildup of ash, but that wasn't the answer either. It was simply concluded you shouldn't run a gas turbine on either pool oil or residual fuel oil, but it'll be a big success if you keep it on high quality distillate oil. There's a photograph of running just 4 hours, only 4 hours on a residual fuel oil by that designation. Now, the Parsons worked with the oil companies, in particular Shell, to see if any other fuels were any other oils were available with lower vanadium and other contents. And this one was one which was the only oil which had very low vanadium, but it had high sodium, and that just made the ash content worse. So these are the sort of results people were saying. Right, the last chapter, nearly, we're on the finishing straight now. What about coal? So after World War II, see, there was a massive demand for energy and very severe winters and blackouts. And it was the UK government decided it was worth seeing if there was a more efficient way of burning coal. Coal was the UK's main indigenous fuel. That was the one to use. They authorised a programme, a budget of £350,000 for the first 2 years of a coal burning gas turbine programme. I have pressed the wrong button. It's back. It's good. Okay, sorry about that. 3 options were considered. One was burning the coal directly in the airflow and passing it through the turbine. 2 manufacturers received money to investigate that, Parsons and English Electric. Separately, a closed cycle system was considered with external combustion. The closed cycle system was patented by Echeverria, and John Brown held the license for that, then Parsons Marine. So they investigated that. And then gasifying the coal was investigated by Metropolitan Vickers. English Electric built a dedicated 2 megawatt gas turbine costing $378,000, which is more than the total budget, but still got built. Parsons simply added a fuel supply to the existing 500 horsepower motor, which cost $44,000. Again, we don't have time to go through the detail of the diagram. You can read it if you look at the slides, but to point out the key features, the coal was delivered as a pulverized powder and stored in bunkers. Usually this equipment was duplicated, so one bunker could be operating, feeding gas turbine while the other was being filled. The coal was filtered and fluidized in the fluidized columns. It had to have a very high coal feed rate because gas turbines are expected to start quickly, and that had to keep up with the pace. And then we had cyclone dust separators before the gas went into the turbine. There's a picture of the coal burning test, one of the arrangements in 1951. Obviously, it looks like the earlier photograph, except you can see the coal equipment on the left-hand side of the picture. The combustion chamber had to be different. And what was done, one of the key differences was you couldn't have swirlers before the burner. There had to be none. If you create a swirl, all that would happen is the coal particles would be centrifuged out to the outer boundary and would just form slag. So this is what was designed. And again, the other change was the introduction of refractory material inside the flame tube. And that's what resulted. So from the first trials, if you look in the center, the square opening is where the burner is without swirler vanes. And what you can see is a combustion efficiency of 97%. But within 50 or 100 hours, you've got slag buildup very, very quickly. You might say today we could have guessed that would happen. But then again, back in 1949 to 51, this was unknown and had to be tested. So we worked with the Fuel Research Station of the UK Department of Scientific Industrial Research. And what they did was create this arrangement where you had shorter sections in the flame tube so that air was coming through to carry away the slag as it formed. And the downstream part of the tube had no refractory layer on it, again, to minimize the amount of slag buildup. And that's what resulted. So it may not look great, but actually it is better than the first one. The picture on the left is after 91 hours running on one grade of coal, and the other is after 65 hours of running on another grade. Just wasn't going to work. This is the dust separator where you have cyclones, 6 cyclones, again acting as a centrifuge to throw out the dust. There was actually an automated system for collecting the particles which were collected in the base of it. Like I said, it could collect 94% of large particles, but not small particles. That's the casing blading. So again, you can see this is after 200 hours operation. You've got deposits building up on the blades themselves. If you look closely on the blade on the left-hand side, where the blade meets the root block, you can see there's a notch being cut. That's because the slag and the ash particles were centrifuged out to the outer boundary and started cutting a knife cut into the blades. But they were eroded, blocked, and it was chemically aggressive. So, and that's the turbine rotor after 200 hours. So you don't have the same notch effect because the particles going to the outer boundary, not the inner. But nonetheless, you still have the same issues of buildup occurring and chemical attack. So down to only 2 slides, I think, at this point. To the left, this is what happened to the power output. If you see the top curve as being for those conditions that existed, had the machine been clean, that's what you would have achieved. And the lower line is what happens when you try to achieve it, passing coal through. You're basically half the output of the machine. And that's with the buildup of only 50 hours, 100 hours of operation. So forgive me for rushing through it somewhat. I have been pushing because I know it's a long talk, a lot of information to cover. But this is the final summary. The gas turbine itself was successful, providing you burn high-quality distillate oil. It was seen as success, and it led to a whole range of other machines. One of them was ordered in 1948, and it was a very large gas turbine generator for Dunstan Power Station in Gateshead, and I'll be talking about that at 6 o'clock today. It's a completely different machine to this, and again, things have moved on, and we'd learned lessons, so it moved on to the next generation, and I'll show you that if you're interested. But we learned about compressor turbine matching and compressor inlet design, the effects of pool or residual oil in coal, and just learned that we shouldn't go that route. One of the things that did happen was, in parallel to this, there was a secret project. Remember, this was talking now 1946 to 54. Straight after the war, anything related to a power unit for a battle tank was still highly top secret. The war had ended, but it was still under secrecy. So there's a secret project going on that most people don't know about. And that actually ran with turbine inlet temperatures up to 950 centigrade. And that was using hollow cool blades. And I'll be showing those as part of the talk later today, if you want to see them. There was a coal-fired gas turbine for a railway locomotive, but this time they didn't pass the coal particles through the turbine. What they did was they had a combustion chamber which heated the exhaust gas coming from the turbine, and then a heat exchanger which then passed that heat into the compressor outlet air. So the gas that went through the turbine was clean and heated. Again, it achieved pretty good results, but it was in competition with many other technologies, and diesel electric proved to be superior. So, but nonetheless, it was a project that was undertaken and completed. Of all of this, by 1960, Parsons' attention focused more to steam turbine generators. We're also making a lot of transformers. The size of the Newcastle works increased threefold. The whole factory increased threefold. Number of employees from 3,000 increased to 10,000. We were making so many steam turbine generators, and the market wasn't as strong. And we had to change the business for gas turbines. We actually had, by 1955, very effective competitive gas turbine generators. And but we realized that the market was different to steam turbines. The customers required you keep many standard parts on the shelf, immediate spares, and you needed much faster production processes. When a large 500 megawatt steam turbine generator took 7 years from contract award to being completed and handed over to the customer, the whole processes had to change if Parsons was going to stay with gas turbines. So it was successful work in the 40s and 50s, but Parsons then decided to wind it up. Parsons also, of course, were heavily into nuclear power, building Calder Hall, most of the plant in Calder Hall the world's first commercial nuclear power station. So there we are.
Thank you very much, Geoff.
Geoff, what I'll do is I'll just repeat to the people online, to everybody online, if you've got questions for Geoff, please either put them on chat, or if you prefer to actually speak to Geoff and put your question directly, please let me know and I'll unmute you.
One thing I should mention is just mentioned on this slide, the first machine is preserved. It's owned by the Discovery Museum in Newcastle, but because the Discovery Museum itself has a weight limit on what it can store, it's actually the heavy store, which is on the Beamish Museum site. So it does exist if anyone ever wants to see it.
Geoff, can I start off with a very simple question for you? When you talk about efficiency of a system, can you just explain how that was measured, what sort of equipment was used, and what sort of accuracy you got on efficiency?
Well, obviously, I don't want to get, I mean, I can speculate. I don't find historically that's useful because obviously, so when it comes to the accuracy of the equipment they made,
Yeah,
I would have to go
changed,
hunting for reports, and I doubt if I'd find them. I don't know what
Right.
accuracy they achieved.
Yeah.
But obviously, when you deal with steam turbines are difficult and gas turbines aren't. The reason I say that, with a steam turbine, the steam eventually turns wet. When it turns wet, the only temperature you can measure is the saturation temperature.
Yeah.
So if it's dry steam, you can measure the temperature in, the temperature out. You know the heat capacity of the fluid, so you can work out how much energy is being removed and get the efficiency. If it's wet, you can't. But with a gas turbine, it never turns wet. So you'd be measuring inlet and outlet temperatures, pressures to work out what the enthalpy drop, the heat drop would be. You know, what's the potential energy? How much energy could you, the maximum you could achieve if everything was 100% perfect from that pressure to that pressure, and then you can measure what's actually achieved.
Thank you. Thank you. Any questions for Geoff?
Okay. Question from David Brown. David says, thanks for the lecture, Geoff. How did Parsons work on gas turbines compare with GT work by continental firms such as BBC and Escher Weiss?
Okay. Well, Brown Boveri obviously have to be credited because they were the first to build a large scale industrial gas turbine. So they were the world's first. Here I've said this Parsons built the UK's first, but BBC were ahead. One of the things that happened at the end of World War II, and I'm going to cover this later on today at the 6 o'clock talk, is that after the victory in Europe, which was 8th of May, 1945, Allied forces went into Germany and Austria to study the technology and obtain key people. So I'm going to cover this in some detail later today because it's very relevant to what happened for Parsons. And one of the things that happened was Parsons sent a team as part of that in July and August 1945. And one of the things that we did was we stripped a complete Brown Boveri gas turbine generator out of a German power station and brought it back to Newcastle and studied it. I've got the photographs, I've got the report, and we didn't learn anything. Now, I don't mean that in any derogatory way to Brown Boveri. They were an excellent company building excellent machines, but a huge amount of effort was also being put in the UK. And yes, Brown Boveri, with having had a lead, will have been better in some regards. All I can say is that when it came to Brown Boveri, we admired the machine, there's no doubt about it. We didn't bring it back for fun. It was worth transplanting it to study it, but it didn't change the design thing. It was all happening in parallel. During World War II, what happened was the government saw that it was paramount the jet engines advance as quickly as possible and industrial gas turbines advance as quickly as possible. And they created something called the Gas Turbine Collaborative Committee. Parsons was part of that. I did rush one of the slides, the one where I showed the picture of the coal-fired coal burning test in 1951. What it said in the words on the left-hand side was, even though war ended, even by 1951, the Gas Turbine Collaboration Committee still continued. So when we were running those tests, our competitors, Metropolitan Vickers, English Electric, as well as the Royal Navy, and anybody who was interested in gas turbines at that time in the UK, who was part of the committee, was present. And no doubt Parsons was present at the other UK people. Echevice, I can't speak with authority about. I know very little apart from the fact they did develop a closed cycle system. I do know of 2 plants in Britain, at least 2, where this was tried out. One was the National Coal Board. The other one, I think, was in Scotland. I can't remember the names, it slipped my mind. But they didn't prove to be superior. In other words, open cycle gas turbines were better than the closed cycle gas turbines. But there's an awful lot of studying. Everybody used to publish their designs openly in papers explicitly, something we would never do today. And people used to study it, and we used to visit each other's factories. We've actually got photographs of Parsons going to Siemens post-war. I'm not talking about investigation after the war, but after Germany became more settled and we're now on friendly terms, we used to go and visit Siemens. We had no link to Siemens as we do today. Parsons is part of Siemens today, but back then it wasn't. So that's all I can really add to that.
Anybody else? Okay, another one online. Chris Hodderan asks, Geoff, a truly outstanding talk with lots of unique, little known information. Can you tell us more about which steel suppliers were developing these advanced alloys? Who made stainless iron? And does this imply very low carbon?
Doug Gass, who is head of materials at Newcastle, would be able to tell you immediately, because all of the names like Mnemonic and Inconel and the like, and the G18 and Immaculate are all trade names of given material producers. I'm afraid I just can't remember the details. And did you say you want to know was low carbon content or not?
He was asking questions about, you use the phrase stainless iron on one of the slides,
Yes,
which has fascinated, and he's asking, does this imply very low carbon?
right. Well, while you're talking, I'm going to go back to the materials table because it's all in there. And I haven't memorized the figures. I'm sorry, that table's a bit much to memorize.
You've had lots of nice thanks as well.
All right. We can maybe take another question while I'm going back through the slides, but
Who did the work on the railway engine? Yeah, was that done at Parsons?
yes, it was a North British chassis with a Parsons power unit. And the power unit was a compressor with a power turbine and a separate turbine driving a gearbox and the transmission to the bogies. And this is covered by a Newcomen Society paper that's published in one of your existing volumes, 1996, by John Boulder. I'm hoping John is online. John Boulder became engineering director of Parsons, but back in the 1950s, he actually worked on these gas turbines.
Yeah.
He was head of the compressor section.
Yeah, thank you.
So just come back to the question. That's the summary of the chemical composition of those materials. Stainless iron is at the bottom. Paleosinetics at the top.
I wonder who gave it the name stainless iron.
Sorry?
I said, I wonder who gave it the name stainless iron. That's the first time I've ever seen
it. Is covered. There are some documents from the 1920s, etc., where it was mentioned.
Really?
I can't remember why. Of course, stainless steel was developed here in Sheffield. It was 1913, I think.
1913, yeah. Brearley, Harry Brearley.
Yeah.
Yeah. And I assume the Hatfields one was Hatfields in Sheffield as well.
Yes, definitely.
Yeah.
I think was mnemonic Henry Wiggins.
Right.
I mean, I have heard the names. I'm just out of practice and calling them up.
Any more questions online, John? You can, definitely.
I'm actually a structural engineer, not a mechanical engineer. So
right.
I understand and have been aware all my life of gas turbines and steam turbines and whatever as a method of providing power. What I'm more interested in is just to go back historically and just say, was this just the natural way people looked at how do you get power out of whatever you use as an energy source? Why a gas turbine? What was the interest in doing that rather than a steam turbine, or were these just the ideas in the 19th century where they were finding ways of producing mechanical energy from fuels?
I think the best way to answer that is to go back to why Parsons developed the steam turbine. He just got it into his head in his early 20s that he wanted to develop. So in those days, reciprocating steam engines were the main high power output prime mover. And they had issues, they had reliability issues, they had vibration issues. He just had in his mind, he would like to develop an engine which was pure rotary power. Didn't know it was going to be a turbine at that stage. He just wanted to invent something. And they just kept looking at ideas. And of course, any company, it's still true today, companies obviously have main product lines which are established, and they're always saying, where do we go next? What do we do next? It's just a case of what could we develop and manufacture that the market would want. There would be a demand. There's no point producing something nobody wants, of course. You know, that's the fatal mistake. But where would there be use?
For sake of argument, with a steam turbine, obviously you produce steam. And I take it, in looking at it, they said, if we compress this and push it through a turbine, we get a greater amount of energy out. Is it the fact that it's the change in temperature that you're taking out the energy out of? Because obviously part of it's got to drive the compressor, hasn't it?
Well,
sorry, I'm showing my ignorance here.
No, it's a very, very. So, and again, what I'm trying to do is giving you answers from the documents of the time, not just my opinion of what I think they were doing. So, give me a moment here to do it this way. When Parsons started on the steam turbine, what did he know? He knew that reciprocating steam engines had a certain efficiency, but were unreliable. Many of them were breaking down quite often. The machine which was most efficient at producing power was a water turbine. So water turbines were 70 to 80% efficient. And that was a nice target. It would be nice if other machines could somehow get close to that. But a water turbine is limited by the water supply. You can only get if you've got a river, that's all the water you've got for producing the power. And in winter it can freeze, and in summer there can be drought, depending on which country you are in the world. So when he developed steam turbines, what he did was the original blades were to try and create water turbine characteristics. So they had lots of stages to have a small pressure drop because water is incompressible. And they had somebody had worked out the equations to calculate how water turbines work. So he simply created a stage, didn't have the equations for steam compressible, but he created lots of stages. So the pressure drop was small, so the volume change was small, and he could apply water turbine principles. But the thing with steam is, where the river is limited in size, you can produce as much steam as you want. You just have to build a big enough boiler. And where you have to go to the river or lake to get the water, you can build a steam plant anywhere, in principle. That's how he developed and got into it that way. And then it evolved into, instead of looking like a water turbine, it looked like the natural design of it then evolved into what looks like a steam turbine. I suspect the gas turbine is the same sort of thinking. What is achievable with a gas turbine? What efficiency will it produce? But it relied upon getting those base technology. You had to get the compressor efficiency up, particularly, as well as the turbine blade efficiency up, and get a net power output.
I take it the gas turbine was of interest because you weren't carting around a boiler to make steam. It was something that was self-propelled, so to speak, within reason, or you put a fuel in.
One of the things that's in the Parsons development reports of the time is the fact that they wanted the machines to be not requiring water. So when you build a steam plant, one of the key things that was built was the condenser, which required a fair amount of water. Ultimately, they actually developed air-cooled condensers, but water-cooled condensers were the way to get good efficiency. That was a lot of water, and the gas turbine gave the prospect for being very portable and very fast starting.
Well, you started at the beginning of the lecture here
Yeah.
by saying that they understood the principle that they needed to get the efficiency up of a steam turbine to much greater to make a gas turbine work.
No, what it said was it's not from a steam turbine. It's just the gas turbine itself. If you want a gas turbine to produce a good output efficiently, you had to have very highly efficient compressor blading and highly efficient turbine blading. So the compressor needed as little power to drive it, and the turbine produces as much power as it could from the hot gas.
Right. So that's just a sort of development of what they'd learned from doing steam turbines. And
I wouldn't say it followed from steam turbine, because a steam turbine doesn't have a similar situation. The thing with a steam turbine, where's the compressor? It's the boiler feed pump. Now, the power required by the feed pump is the integral of volume and pressure, and it was the VDP and PdV. And what you'll find is, because water is incompressible, the amount of power you need to drive the pump is only one. So if you've got a 500 megawatt steam turbine, you've got 5 to 10 megawatts powering the pump, not 200 megawatts, which is what you'd have with a gas turbine of that size. So you didn't have the same issue with the steam turbine. So I don't think it evolved that way. It was just gas turbines gave another opportunity to see what could be achieved.
so is the compressor more related to the fact that in a gas turbine you needed to concentrate whatever the fuel was before you burnt it, and you haven't got quite the same necessity with a steam turbine?
Yeah, I mean, the gas turbine has two issues, which is why steam turbines are still with us today. The two issues are, first of all, you're going to discharge to atmosphere. So the outlet pressure is going to be 1 bar or thereabouts. Now, the amount of energy that you can extract from any thermal engine, whether it's a petrol engine, diesel engine, gas turbine, or whatever, the amount of energy you can extract depends upon the pressure ratio, the compression of the engine, in effect. So because the outlet pressure is only 1 bar, this machine was it 51 psi? So you only got 3 to 4 bar. So it's 4 to 1 pressure ratio. Modern gas turbines are often somewhere between 20 and 100 to 1 pressure ratio, but a steam turbine can achieve 20,000 to 1 because this exhaust steam can be condensed to water and create a vacuum.
Right.
And the other side is the fact that the compressor, because the air in the compressor is compressible, when it comes to determining how much power is required, you're using, in these machines, 60, in the 1940s, you're talking 60 to 70% of turbine power was used to drive the compressor.
Okay, thank you. I was never any good.
That's
at
why
thermodynamics.
That's why steam turbines still exist.
Okay.
First a comment, Geoff, from David Brown. Like me, he looked mnemonic up on Wikipedia. First batch of mnemonic was produced in 1941, named mnemonic 80, produced by Mond Nickel Laboratories,
Yes.
Newcomb and paper by
Yeah, that sounds
Darling,
right.
83, 84. The sort of question comment from Chris Hodder, and it's a long one, so I'll do my best to read it right.
Okay.
British Gas, with UK government and EU funding, returned to the coal gasification option for power generation, using the British Gas BGL gasifier still being built in China.
Mm-hmm.
I'll scroll down a bit further. In late 1980s, no ash formation, but the sulfur from the coal as SO2 corroded through the GT blades in only 500 hours. This shows that the gas had to be desulfurized before it could be used.
Yeah.
Yeah. And the final one is from Bernard Caddy. Oh no, it isn't.
And of course, in everything you've just said and everything I've said, the one thing that didn't exist in those days was the fact that you can't burn a fuel today which emits CO2.
Yeah.
So, and you can't escape that with coal. So that's no matter what you do.
Coming from Bernard Caddy, it's fascinating that gas turbines started as powering torpedoes. I imagine that the exhaust trail was a problem. Do you know when and why torpedoes moved away from this power source?
I don't know.
I can also add for Bernard and those online that they were also testing them in a public lake.
What I can tell you is what Parsons was happening with Parsons. So Charles Parsons was the youngest son of the 3rd Earl of Ross. who was a great astronomer. And Parsons always wanted, while he came from an earl, a family with an earl and with money, didn't want to just live a privileged life. He wanted to be acknowledged as an engineer. And so he's initially, before he became a partner, went into business properly. He actually went to what's called a premium apprenticeship. So this is becoming apprentice engineer, but the premium part means he's coming from a privileged family, but nonetheless, he was an engineer, and he worked with William Armstrong in Newcastle, and he worked at Kitson's of Leeds. And it was while he was at Kitson's of Leeds, he was effectively an apprentice engineer, but he had to create something, and he created this torpedo engine. And Kitson's liked it. Now, when he actually moved to Clark Chapman in 1884, he had about 500 torpedoes to take with him. So they were making them in some numbers, but we don't know more than that. We don't actually know how many were sold or worked or whatever. Of course, Whitehead's developed the torpedo. It was only 3 years earlier, I think, 1878, I think.
Yeah.
And of course, there were other methods of driving them. Parsons sort of dallied with it, but his heart was in other things. He was really driven to create this pure rotary motion. He created a thing called an epicycloidal engine, which was an engine with 4 pistons arranged in a cruciform, opposing each other. And the crankshaft rotated and the crankcase rotated. To create that was a type of steam engine. It wasn't pure rotary motion because it was following an epicycloidal path. But he was just determined to get pure rotary motion. And he wanted to get rid of belt drive as well because they were unreliable. He wanted direct connection to whatever was being driven.
Another comment online. Just to add to that, Kitson's house overlooked Roundy Park Lake.
Mm-hmm.
And Roundy Park Lake is where Parsons did his testing. In the 80s, I was involved in draining the lake to do a new outfall, long story.
Yeah.
A search was made just in case anything was visible in
Yes.
the bottom of it for it, but nothing was found. Well, nothing like that was found.
Would it be worth trawling the silt just to save much of that?
Yeah, there were all sorts of interesting things found there. One from Chris Hodderan. Again, the EU funded 2 full-scale coal gasification GT demo plants, about 500 megawatts in the 1980s at Begunum in Holland and Pruta, somewhere in Spain. Just Google the plant names. Both ran at least until 2010. GE Turbines, I think, world's first commercial plant at 110 megawatts. Texaco gasifier and GE turbine was cool water. I'm going to have to scroll this down. In the Mojave Desert, California in 1982. I did a huge plant using German Lurgi gasifiers called Dakota Gasification, runs daily at Great Plains in North Dakota, but this feeds the gas grid, not gas turbines. Any comment?
No, I just acknowledge what he's seen. He's releasing another project.
Chris is the expert. Chris is the expert on submarines.
Yeah, well, Chris and I have talked a lot over the years.
Geoff, the turbine that we've got in Kelham here, where does that fit in this story?
Oh, yeah. So you're talking about, switch off gas turbines. We're now on steam turbines.
Yeah.
So Parsons developed his first steam turbine generator, which was machine number 1 in 1884.
Right.
And that was retained in the works for experimental use, or investigative use. Yeah. So machine number 1 is in the Science Museum in London. Now we've still got the full list of machine numbers and orders. Machines number 2 and 3 in the order book are blank. Now what that means, because you've got machine number 4 here.
4, yeah.
So machines number 2 and 3 being blank, what did it mean? It meant it was either contract numbers that were set aside for building an experimental rig, or some manufacturing equipment, or a different kind of product, not a steam turbine. But basically, machines number 2 and 3 were not steam turbines. Machine number 4 was the next steam turbine after machine number 1. and it was the first steam turbine generator in the world to be made for a customer's use, productive use. So it was actually installed on a yacht called the SS Earl Percy in 1885. And I was astonished to find you had it, because what happened was the Earl Percy sank in 1889.
Yeah. But
the turbine generator must have been taken off. Now, what I found is I'm going through the history work I'm doing. I'm working with the Tinyware archive, and I'm going through the original Parsons records. And number 4 machine was actually loaned to Parsons in Newcastle for the centenary celebrations in 1984. And we investigated it and checked it out in detail. And it is machine number 4 for real. There's no doubt about it. Or no, it's the second turbine they ever built, or the first production turbine for customer use.
Thank you.
So, yeah.
Thank you. Well, thank you, Geoff, for that wonderful talk. And David's going to give a vote of thanks.
Yeah. Thank you for your patience and time.
Geoff, a very high-powered presentation. Myself, I've been involved in turbines, Siemens compressors and such like, and never really understood them. I wish I'd have had this presentation beforehand, but a lot of knowledge is being accumulated, by yourself, and it's providing the Newcomen Society, not least South Yorkshire branch, with some very, very interesting presentations. So on behalf of those assembled here and our friends on Zoom, I'd like to thank you for the first part of your delivery, and look forward to the second part later on this evening.
Thank you very much.
So thank you very much.
Yeah. Before we go offline, I'd just like to say one thing. There is another talk this evening. It is about gas turbines, but if you think it's going to be like this one, it's not. So it is going to be very different. One little thing I want to touch on is, that at the end of the war, the Americans got Werner von Braun and developed moon rockets, etc. Very knowledgeable man, and it did boost their rocket program. The British didn't go hunting for moon rocket men. They went hunting for German and Austrian gas turbine men. And 6 of them ended up in Newcastle. If you'd like to know more, turn up later and I'll tell you all about it.
Very interesting.
Thanks, Geoff.